Alright, here we are in section 2.4, and 2.4 is going to bring up the idea of correlation, specifically linear correlation. And correlation exists between two variables when the value of one variable and the other variable are somehow associated with one another. And so we have linear correlation when that association between the two variables can be expressed as a line. That is, as it seems like they're lining up, that there's a linear pattern to the data. And so what I have for you is a picture, and these pictures are what the book refers to in all statistics refer to as scatter plots. So scatter plots plot data together. So you can see this very first one. I don't think I can make it bigger than what it is right now, but it's plotting. Apologize. It's plotting waist circumference to arm circumference. And what they did is they took a person's weight and arm, and they allowed weight to be the x-axis and arm to be the y-axis. And they were looking if there was a general pattern. In the next one, they looked at weight, somebody's weight in kilograms, and also their pulse rate in beats per minute. And they did what's called a scatter plot. They said, okay, this person weighs 75 kilograms and their pulse is 50. And they put a dot in the appropriate place. And so all those dots represent individual, in this case, people, right? And their and the data that they were taken from them. The book's going to have you look at some of these pictures and decide whether there's linear correlation going on. And what I want you to see is that in picture 1, the red one, maybe I'll use a red pen to match, this one does appear to have linear correlation. It does appear that we can get a line that goes right through the middle of that data. It's not going to be perfect, right? We're not going to be able to get everybody, but in generality, it does look like it's increasing over time, that a line would do a good job of describing that data. I was going to say, I apologize that I can't write on top of that picture, but I don't think I can. If I go over to the blue one does not appear to have linear correlation. In fact, it doesn't appear to have any type of correlation. There are different correlations. You can be quadratically correlated if it looked like a parabola, or exponentially correlated happens a lot. But linear correlation will follow a line, and that's the one that we're focused on both here in 2.4, and then also those couple sections that I'm grabbing out of chapter 10 will reinforce this idea as well. And so first thing is to get an understanding of what we mean when it's linear correlated. We just mean that, hey, when I do the plotting, it seems to be following a linear pattern. And that linear pattern could be going down over time as well, right? It doesn't have to be going up. And so, as you know, with math, we don't necessarily only want to rely on pictures. We want to rely on measurements, right? A measurement that would let us know whether something's linear correlated or not. And they have one. And it's called the linear correlation coefficient. And we'll look at that in just a minute. What I want you to see, though, before we get there, is with just a very few pieces of data, it's hard to tell whether there's any correlation. But as you get more and more in there, if they start to have a pattern, then you can start to justify the correlation. So this R factor, when you see its formula in chapter 10, it's going to be dependent upon going to be dependent upon N, the sample size. Because those same points that I initially did, if I start doing other points and there doesn't appear to be any pattern whatsoever that's growing or decaying over time, then we'd say it's not linear correlated. And so we'll have different benchmarks based upon the size of the data. So I have a definition for you, the linear correlation coefficient. So let me come in here and move this chart down so you're not focused on that too much. So the linear correlation coefficient is denoted by the letter R. And what it does is it measures the strength of the linear association between the two variables. So here's some things to know about R. R can be positive and R can be negative. A positive R means that the line that best describes it is going to be positive in slope. It's going to go up over time. A positive slope line would increase as you look at it from left to right. A negative r means the exact opposite, that it's going to drop over time. So these two right here, their r value would be a positive value. This one right here, the r value would be a negative value. This one right here, it's hard to know whether it would be positive or negative, but it would have some value in there. Although r tells us about the slope, it is not the slope. So every once in a while, I'll have somebody say, well, hey, r was equal to 0.958. That means it's linearly correlated and the slope is positive and is 0.95. The slope's not 0.95, right? R does not equal the slope. And so I just want to stress that for any that might misassociate those two. It does tell us that it's going up, but it doesn't tell us at what rate at all. Because r's have a maximum bound. I didn't mention that in here. I forgot about that. So I'll write it up above here. R is bound between 0 and 1 the way they have it described. The highest it could ever be is 1, and it can be flat out 0. 1 would mean that there's perfect linear correlation. So an R value of 1, I'll put that, I can't put it right here. Let me come down here. An R value flat out equal to 1 means perfect linear correlation. What would that look like? It would be a situation where you did your scatter plot and things lined up perfectly. An R value equals -1, would mean perfect correlation, and it's going down over time. And remember, it has no bearing of the slope, so it could be sloping, very steeply or gradually. It wouldn't make a difference. So hopefully that makes sense. So you're hoping your R value is 1, but it never really is unless it's kind of just made to be, right? You're using a particular function, but not with data that's collected. Data that's collected is never really perfect in that sense, and so we don't really expect to have perfect linear correlation, but we do expect to have correlation. So for example, this red one up here that I said had linear correlation, its R value is not going to be 1. We determine whether two variables have linear correlation. So I'm looking at that second to last bullet. The two variables have linear correlation if the absolute value of R is, and I put in quotes, close to 1. We determine if it's close to 1 by using a chart. And this is the chart that is here in 2.4. There's a little bit of a stronger one that they use. I shouldn't say stronger. It's the same chart, but it has more options on it as we get into chapter 10. So if there's 4 pieces of data, you need an R value of at least 0.950 or higher, right? I guess I said at least. But if you have 11 pieces of data, it can be as low as 0.602 as an R value. Anything above 0.602 would be close to 1, right? And what's saying, and if you had 12 pieces of data, you could get by with any R value that's greater than 0.56. And so what the book should do is they should tell you, hey, we looked at, let me not write it like that. Let me actually write out a sentence. I was going to do it all in symbols. We looked at 12 pairs of data and found that the R value is what they call it. Sorry, I drew a blank on that. The R value is 0.612. And let me make it negative, just for emphasis. Do we have linear correlation between those two variables? So let me remind you, we have linear correlation if the absolute value of R is close to 1. So the absolute value of -0.612 is 0.612. So the question is 0.612 close to 1? Well, you and I can't know that unless we go to a chart. And so let's go to this chart. Now, we're not going to look anywhere on this chart. We're going to look at a very specific place. We're going to be looking at the last row. Why the last row? Because we have 12 pairs of data. If you want to know what we do if we have more than 12 pairs of data, we use a bigger chart that's in the back of the book, like they'll do in chapter 10 when we get to those sections after chapter 3. So 12, we need at least 0.576. So because 0.612 is greater than 0.576, we do have linear correlation between the two variables. We would be able to find what they call the regression line that would describe it basically is also called the line of best fit, but it basically goes right in between all those points. What would change if I said this? We looked at 8 pairs of data and found their R value to be negative 0.612. Is there significant linear correlation? Now they'll put that word significant in there, so I wanted to too. Significant just means from a statistical standpoint, does it look like they're linearly correlated? Is there strong evidence of that? And there is, provided our R value is big enough. So I use the exact same R value of negative 0.612. We always consider the positive of it. And so we're going to come up here and remember how many pairs of data we had? We had 8. 8 pairs of data, what they call the critical value, the value that's the benchmark for close enough for 8 pairs of data, you can see it right here is 0.707. So I'm going to word this a little bit differently. We have significant linear correlation only if 0.612 is greater than 0.707. That is, if the R value is more, let me not word it like that, let me make that even better, is closer to 1. Remember, than 0.707. Okay, that's how we know we have significant correlation. If we're close to 1, how do we know if we're close to 1? If we're closer than the benchmark. Is 0.612 greater than 0.707? No. So we do not have significant linear correlation. Okay, and so there's going to answer no sometimes, yes some others with the exact same numbers. What was the difference? The number of pairs of data was less this time, and so there was a stronger benchmark. With less data, it's got to be more in line for us to start to say that there's a pattern to it that seems to be linear. When you have a bunch of data pairs, you can get by with very low R ratings coming through, and so it really all depends upon your sample size as to what that benchmark is for close to 1, which is the reason why I put it in parentheses. But give this section a shot. Let me know if difficulties arise and we'll get them addressed.